Hello everyone, thank you for watching this video lecture. In today's lecture, we're gonna study one interesting algorithm that is called as Simulated Annealing Algorithm. In the previous lecture on hill climbing and gradient descent, we saw how optimization methods or search methods try to move toward better solution by following the slope. If we are going to the maxima, right, we go proportional to the gradient descent, and if we are interested in the local minima or global minima, we go opposite side, negative, right? So the idea is simple. Always we move to a better solution compared to where we are now. But there is a problem. So as you can see here, if we start at this point and we are interested in maxima, so we can never reach to here, but we will go to here. So this is the global and this is the local maxima, right? We are interested in here, but we will start here. And if we start at this point, we will go to here, right? And the same thing for the local and global minima, like this point, like this point, like this point, okay? So this is the problem, because those algorithms that we study, they are greedy. They do not allow us to explore worse moves, so we might get stuck too early in local minima or local maxima. So simulated annealing overcomes this problem by sometimes allowing something that we call them as bad action, right? So in here, instead of, so for example, if we are here, instead of moving to this part, we will come to this part, and from here we go to global maxima. It means occasionally we accept a worse solution. Worse solution, it means instead of going, for example, for global maxima, instead of going proportional to the gradient, we go to the opposite side. So we move downward instead of always upward, or vice versa in case of gradient descent. The key idea is that these bad actions are controlled. Early in the process, we allow more exploration, but as the algorithm runs, the acceptance of bad moves decreases. This balance between exploration and exploitation is what makes simulated annealing perfect for escaping local optima and approaching the global maximum or global minimum. Originally, this concept of annealing is a process in metallurgy where metals are heated and then they are slowly cooled down. In such scenario, we allow them to reach a state of minimum energy and maximum strength. In computer science, we borrow this concept as a simulated annealing, right? Simulated annealing. So in here, the temperature is an analogy for randomness in our search process. At high temperature, the algorithm behaves like a random search, freely exploring the solution space. As the temperature is gradually reduced, the randomness decreases, and the algorithm starts behaving more like a greedy descent method, and it will focus only on improvements. This slow cooling schedule helps avoid getting trapped in poor local minima and instead guides us toward a near optimum solution. So simulated annealing is especially powerful for solving both unconstrained and bounded constraint optimization problems where traditional gradient-based methods may fail. So here we're gonna study the algorithm. So we can call it as a search algorithm, or we can call it as an optimization algorithm. It can be considered as a modified version of stochastic hill climbing. Stochastic hill climbing maintains a single candidate solution and takes a step of a random but constrained size from the candidate in search space. Then, if the new point is better than the current point is replaced with the new point. This process continues for a fixed number of iterations. Simulated annealing executes the search in the same way. The main difference is that new points that are not as good as the current point, we call them as worse point, are also accepted only sometimes, not always. When we accept these worse points, a worse point is accepted probabilistically, where the likelihood of accepting a solution worse than the current solution is a function of the temperature of the search and how much worse the solution is than the current solution. So here we can see the algorithm. First, we go for initialization, simulated annealing algorithm, problem, and schedule, and then we return a solution state. The input is problem, schedule, and a mapping from time to temperature. And we have local variables like current node, next node, temperature. So we start from an initial or current for a given problem. Then we define a schedule that maps time or iteration to the temperature T. In this way, we can control the acceptance of our solution. So then we go into the loops, so like T from 1 to infinity. Then we will stop where the temperature is equal to 0, right? Infinity doesn't work everywhere. So it doesn't mean we go for infinity. So we will stop when T is equal to 0. Then we will update the temperature and we set T is equal to schedule T. Then when T is equal to 0, we will stop it. Then we will generate candidate, or we randomly select a successor state, like the next from the current state, neighborhood. Then we compute the energy difference, that is delta E, value of the next minus value of the current. We measure whether the new state improves objective function or not. If delta is greater than 0, we accept next as the new current state, it means improvement. And if delta E is less than or equal to 0, we accept the next probabilistically with the probability of E in power of minus delta E divided by T. This allows to escape from local minima. We repeat this iteration until the temperature reaches 0, and we will stop here. We gradually reducing the likelihood of accepting worse actions, and in this way we converge toward a near optimum solution. So in summary, we explore randomly at high temperature, gradually focus on improvement as temperature decreases, and in this way it allows us to escape from local optima early on and converging to global optima. Now, let's focus on the temperature parameter in simulated annealing. Temperature controls the balance between exploration and exploitation. In exploration phase, bad actions are allowed, but in the exploitation phase, bad actions are limited or avoided. When the temperature is high, the algorithm is more likely to accept worse solution, and this allows it to explore the search space more broadly. It's like a random search. When the temperature gradually decreases, the algorithm becomes more conservative, favoring better solution and behaving more like a hill climbing search. By decreasing the temperature slowly, simulated annealing increases the likelihood of finding the global optimum with the probability approaching 1. So here is one example. Suppose this function is f(x) is equal to x squared plus 10 sine x, right? And we are interested to find the global minimum here. Suppose we start at this point x is equal to 6, right? So x0 is equal to 6, and we consider temperature is equal to 10. And also cooling rate or alpha is equal to 0.95, right? So we are in here. First, we will calculate f6, right? So f6 is here. f6 is equal to 6 squared plus 10 sine of 6, right? So, if you do sine of 6, something like minus 0.2794, then if you do this calculation, you will come up with 32.6, right? Then our x is 6, our t is 10, and our fx is 33.206, right? So at the first step, we generate a new candidate. So how to generate a new candidate? X new is equal to 6 plus random value, right? So we get a random variable like random dot uniform from -1 to 1, right? Suppose we got 0.5 out of this random, and we call this one as U1. Then the next x is equal to x new is equal to 6.5, right? So we will calculate the f of, based on this equation, based on this formula, we calculate f 6.5, and this is equal to 44.4, right? So we will calculate the delta. Delta is equal to the new one minus previous one, right? 44.4 minus 33.206, which is equal to 11.194, right? So this 11.194, it means delta is greater than 0. So then we will calculate the acceptance probability. The acceptance probability is equal to E in power of minus delta divided by T, which is equal to E in power of minus 11.94 divided by 10, which is equal to 0.332, right? We try another random number here, like for example, round dot round, and for this one is from 0 to 1, right? And we call it down as U2. Then we will find this value, right? If U2 is less than this value, then we accept, otherwise we reject. Suppose this value that we have generated is not less than this one, so we reject. Okay, so we rejected this value, it means we will not go to this 4.4, and then in here we will reduce the temperature, right? So temperature T multiply 0.95 is equal to 9.5, right? So let's try the next step. So in here we didn't move, right? In the next step, we go for, again, like this one, x new round info, round uniform -1 to 1. Suppose this time we got U1 as minus 0.7, right? So x new is equal to 6 minus 0.7 is equal to 5.3. Then based on this equation, we calculate f of 5.3, which will be 19.77. Then we will calculate delta. Delta is equal to 19.77 minus the previous step, this one, 33.206, which will give us 13.6, right? So it will be minus. Because delta is less than 0, so we accept. When we accept, then we say the new x is here. So we will move to 5.3, and again we will decrease the temperature, right? So 0.95 9.5 multiply 0.95 will be equal to 9.025. So as you can see here, we will repeat these steps, 1, 2, 3, 4, 5, 6, 7. We have to repeat all these things. Finally, we will come to here. If this is gradient descent, we will stop in here, in global minima. By using simulated annealing, we can come to global minima. In simulated annealing, the amount of time allocated to the algorithm directly affects the solution quality. If we allow the algorithm more time, it can explore the search space more thoroughly, and it is more likely to find an optimum solution. Conversely, with limited time, it may only find suboptimal solution like local minima. These properties make simulated annealing suitable for complex optimization problems in various applications like scheduling, airline scheduling, VLSI, CPU design, configuration, and etc. Okay, thank you very much for your attention. This simulated annealing almost like the hill climbing, but in each step, the next state is randomly selected. If the selected next state is better than the current one, we move to the next step. Otherwise, we move to the next state with the probability of what? Probability of E in power of minus delta divided by T, right? This probability tells us to take a bad action or not. If the selected next action is a bad action, the probability decreases in an exponential manner. So the probability also decreases while the temperature decreases. Thank you very much for your attention. Please feel free to ask me your questions. Thank you and see you in the next lecture.